Welcome, Physics 1. It is I, Dr. Neutron, streaming to you from Galaxy ESO 461-036. This is an irregular galaxy located in the Great Void. It's an empty region of the universe that's 150 million light years across. It's the only confirmed galaxy in this region. To give you a clue, our own Milky Way galaxy is 150,000 light years across, much less than the Great Void 150 million years ago. That means that if light left this galaxy and traveled to Earth, there would have still been dinosaurs, if there were in fact dinosaurs alive on Earth 150 million years ago. But it's unlike our own Milky Way because it's not spiral shaped. Andromeda, our nearest neighbor, is also a spiral galaxy, which is consuming another galaxy, as is the Milky Way, possibly something to consider. I enjoy pictures from the Hubble Space Telescope because it helps me to appreciate the vastness of space. The universe is big, and we are very small. Maybe you have some trouble in your life, but just remember, we're all just specks of dust floating through the cosmos, which is mostly empty space. So whatever your trouble is, remember the words of a great man, this too will pass, whatever it is. So don't worry, be happy. Vectors. What are they? What do they mean? Vectors are important, almost as important as keeping things in order. Dr. Neutron loves order. That's why I've decided to construct my own vector. And if you've ever tried to draw a vector, oh no. Okay, we're gonna have to actually look at it to make my own vector. This page is ruined. Ruined, I tell you. I can make my own vector on this piece of paper. I'll make a big vector. And a bigger vector. You thought I was going to say a smaller vector. No. There. I've done it. I've made some vectors. One is big and the other is bigger. In order to make your own vector, you're going to need a scissors. Once you have your scissors, you can cut out your vector. So, constructing my vector. Here it is. This is my vector. Make it a vector. We can do it. We can make a vector. As an experimental physicist, it's always possible to make a vector. Anyone can do it. You can construct your own vector. It's not just a piece of paper. No, it is a vector. So, as you construct your vector, and think about the vastness of space and what the velocity vector of our galaxy. The Milky Way moving through space. Where is it moving to? Where did it come from? How fast is it moving? Is it rotating? Maybe it's spinning. Things to think about as you're constructing your own. We can do it. Now, you can be amazed because I have constructed a space vector. I've made my own vectors. So if I position my vectors, I can add them together. See, here's one vector. No, you can't see. Okay, so here's my two vectors. It's not good. I've made my two vectors. They're pointing in different directions. I can add them together. See, vectors have magnitude, which is the length of your vector. Yes, magnitude. And they also have direction. So your vector is pointing, maybe it's pointing at this galaxy over here. Yes, there's a galaxy. There's my galactic vector. Yes, I've done it. We can add it to another vector. There it is. It's much more dramatic if I did it in class. Imagine you're standing in the classroom while I constructed my own vector. Amazing. I know what you're thinking. There's a vector in your pocket, Dr. Wisby. How did it get there? Let's talk about physics. Chapter 3, Vector and Motion in 2 Dimensions. We are going to attempt to get through it. College Physics A, a strategic approach. If you're in my class, you know this book. If you didn't, all problems we do will be from this book. Let's go through the chapter. Here is an intro of what we will study. These are videos for the chapter. You should watch them when you can. They're very good. I haven't watched them, but I'm sure they're great. So, chapter 3, Vectors in Motion in 2 Dimensions. You want to learn more about vectors, how to use vectors to analyze motion in 2 dimensions. We have been doing a lot of problems with vectors, and they are extremely important. The mountain lion jumping, we needed to know our X and Y vectors, components of the vectors, and also we need to know the magnitude and the angle. We can analyze motion with vectors. All right. The dark green vector is the ball's initial velocity. The light green component vectors show the initial and horizontal velocities. Okay. So here is this one is Vy. Then over here is Vx, and we have some angle theta there, and this is going to be V. We could transport Vy over here, okay? So this is Vy. We just moved the same vector over to the side. There it is. Oh, too many arrows. Need to erase those. There we go. We can move Vy over there, and then now we have a right triangle right here. So Vx, Vy, and of course, we then have V equals Vx squared plus Vy squared. That's going to give us the magnitude. Then, of course, if we want to get the angle there, we can use tangent of theta. So tangent of theta will equal Vy over Vx. These two equations, very important. And we're going to learn to describe motion in terms of qualities such as velocity, distance, and of course, acceleration. So, I'm going to erase. Erase all my words and my drawings. There we go. All right. Of course, we had the problem of the fish jumping up the ladder. It has an X and a Y velocity. And our fish will fly out of the water with a big velocity and it will make it up the ladder. And we can find its X and Y components. So we're going to use vectors to solve projectile motion problems. We're going to look ahead at circular motion, and if a vector is changing directions, it might have a constant magnitude, but if the direction is changing, it is accelerating. When you're on a merry-go-round, you feel a force, and that is due to the acceleration of your velocity vector. So your velocity vector is changing directions. Okay, so the acceleration comes from a change in direction of your velocity vector, which leads to a centripetal force. We'll learn how to determine magnitude and direction of the acceleration for an object in circular motion. Okay, free fall. If we throw an object up in the air, acceleration is always constant. It doesn't change. And so that means that our velocity is going to change. So our vector down here is these vectors are equal in magnitude and opposite in direction to the vectors on the right when the particle is coming down. Acceleration never changes. All right, so let's take a little problem here. A conceptual problem. A player kicks a soccer ball straight up into the air. The ball takes 2 seconds to reach the highest point. Approximately how fast was the ball moving when it left the player's foot? Well, if acceleration is a change in velocity, the acceleration is about 10 meters per second squared. So that must mean that in 2 seconds, every second it's going to slow down if it's going up by 10 meters per second. So it will decrease in velocity every second at 10 meters per second. So that would mean that the answer has to be D, so it's 20 meters per second. Take 2 seconds. Okay. Another question, reading question 3.1. The blank of a vector is always a positive quantity. Well, x could be negative. You could have a vector in the negative x or the negative y direction, so that can't be it. The direction D, the direction can be negative. The only thing that can't be negative is the magnitude. Magnitude of a vector is always positive, but it can point in any direction. You could have a negative component or a positive component. So the magnitude. All right, reading question 3.2, x is positive, and that's ax, the scalar is positive, which is, this is the magnitude of the vector ax. Ax is positive if ax is directed, blank ay is positive if AY is directed what? Okay, so AX is positive if AX is directed, and usually in this one, let's draw a little picture. The convention, of course, is that X is positive going this direction, okay? So X is positive that way, so that means it's going to be to the right, and AY is positive if A, the vector, is directed upwards. So the positive Y direction is always up. That's the convention that we use, okay? So the correct answer is A. It's going to be right and up. So AX is positive if AX is directed right, and AY is positive if AY is directed up. Okay. The acceleration of a cart rolling down a ramp depends on what? Let me erase my marks, get a clear view of what is happening, and let me make sure everything is working correctly. Okay, here we go. Don't want any problems with Zoom. Look, my vectors are still there. Hooray. All right. The acceleration of the cart rolling down a ramp depends on A, the angle of the ramp, B, the length of the ramp, C, both the angle of the ramp and the length of the ramp, or D, neither the angle of the ramp or the length of the ramp. Well, I don't think that the length of the ramp determines its acceleration. Acceleration is always constant, but it does depend on the angle. So the answer for this one is the angle. The length of the ramp doesn't matter. The angle does. The steeper the angle, the higher the acceleration is going to be. So if you have a small, very small angle, the acceleration is going to be low. Let me draw a picture of what I am talking about. I'm going to use some lines here. Okay, so if we had a perfectly flat line and we had some particle, okay, then let's say our cube here. We'll draw a cube on this box. Okay, so if this is some object, and we're going to approximate it by Q, by a cube, okay, then the acceleration is always going to be down, but here it's not going to accelerate. Gravity's pulling it down, but the block is not accelerating because it's perpendicular to the acceleration. If, on the other hand, I raise this by some angle, okay, so let's say I have a small angle here, and I have another block over here. Here's a block. Okay. Gravity is still going to be pulling it down this way. Okay, there's gravity. But now, since there's a little angle here, let's draw our angle. We've got a little bit of an incline. So there's going to be a force, an acceleration. We haven't gotten to forces yet. But my acceleration is going to be going down this way. And if I draw components, so this is going to be AY here. So this will be A, my acceleration, okay? And if I break that up into components, okay, I'm going to have a component of my acceleration going this way, right? And we can call this way, well, we can call it whatever we want. So there'll be a component over there. And then there's going to be another component over this way, okay? So, and then this will be, this is of course a right triangle right there. There's a 90-degree angle. Okay, so that means I've got some angle in here. Okay, so there's an angle in there. That's going to be theta. And the one that I'm interested in over here, the one that I care about is this guy right there. Because that is the acceleration in the direction that my block can move. And so if I want to find that, okay, then this vector over here is going to be A, the hypotenuse of my triangle is A, times sine of theta. That's the opposite side right here. So up here, I'm going to make this bigger. There we go. So up here, then that's going to be my the magnitude of my acceleration. It's going to be A sine of theta. Maybe that was too thick. That was definitely too thick. Okay, it was good for the picture, not so good for writing letters. Okay, so A, there it is. It's going to be A sine of theta. There it is. That's my acceleration. And so the angle of the ramp does matter. The length of the ramp does not. All right. Let's erase everything quickly. Erase it. Oh, zoom. Okay. All right, there's our angle. All right, moving on. The acceleration vector of a particle in projectile motion, A, points along the path of the particle. B is directed horizontally. C vanishes at the particle's highest point. D is directed down at all times, or E is 0. So this is the acceleration vector of the particle in projectile motion. And there's a lot of important things going on here. Let us draw a projectile. I'm going to use blue this time. Okay, here is our projectile. We are launching it at some angle here, and our projectile here is going to be this boulder. We launched it from our trebuchet catapult. I love catapults. Something fun in mechanics. You can build a catapult. Well, one thing to know is that our x velocity, Vx, never changes. Vx is always constant. And let's draw the ground here. Here's our ground. Okay. This way is going to be Vx. We'll call this Vx. This is Vx. No, not Vx. It is the x-axis, not Vx. So this axis is our x-axis. Y is going to be going up this way. Here's our y-axis. This way is y. There's y. Over here is x. And once the projectile is launched, Vx doesn't change. There's no acceleration in the x direction. Okay. As it gets to the top, Vy goes to 0, but our acceleration vector is always pointing down. Gravity always pulls objects towards the center of the Earth. And so this is going to be minus 9.8 meters per second squared. That's always pointing down. And so our V velocity is going to change. When it gets to the top up here, our velocity in the y direction is going to be 0. Okay, so what is true here? The acceleration vector of a particle in projectile motion points along the path of the particle. No, that's not true, because acceleration always points down. Is directed horizontally? No, there's no horizontal acceleration because we're ignoring wind resistance. V vanishes at the particle's highest point? No, gravity is always on. You cannot turn it off. Would be cool if you could, but you can't. So it's directed down at all times. So the answer is D. It is always pointing down. Gravity never changes. It's always pointing towards the center of the Earth, which is what we call down. Okay, so moving on. The acceleration vector of a particle is in uniform circular motion, points tangent to the circle in the direction of motion. Let's think about that one. The acceleration vector of a particle in uniform motion. The velocity is tangent to the circle. Or let's look at B. Points tangent to the circle opposite the direction of motion. Or C is 0. Or D points towards the center of the circle. Or E points outward from the center of the circle. Well, it's not in the direction of motion. So uniform circular motion means the velocity is not changing. Magnitude does change direction. Velocity changes direction. The velocity is the thing that points tangent to the circle. If it's moving in a circle, there's something pulling it towards the middle. That is the acceleration, so it points towards the center of the circle. Okay, using vectors. I've got them right here. Using my vectors. Oh, that was clever. Oh yeah, all right, using vectors. A vector is a quantity with both size, has magnitude, and a direction. The vector is always pointing somewhere. Vectors like to point. They're so rude. Vectors like to point. They point. Look, the vector's pointing at my head. There we go. Yes, vector. This vector's pointing at my nose. All right. The figure shows how to represent a particle's velocity as vector v. V, if it's a vector, we draw this arrow above it, which tells you, hey, it's pointing at something. It must be a vector. Yes, that's the name of the vector. V, we call that's velocity. We use v for velocity. And the magnitude of our vector, we write v, but without the arrow above it. The arrow is muy importante. Yes. It has a direction. The vector is always pointing some direction. Okay. If it's a vector, it has a direction. If it's a scalar, it does not have a direction. Which way are 5 oranges pointing? I don't know. They don't point anywhere. I just have 5 of them. It's not a direction. That's a scalar. Okay. If I am moving at 10 meters per second away from my house on a skateboard, that is a vector. Okay. Particle's speed at this point is 5 meters per second, and it is moving in the direction indicated by the arrow. Yes. Okay. Using a vector, the magnitude of a vector is represented by a letter without an arrow. That's the magnitude. In this case, the particle's speed, the magnitude of the velocity vector, v, with an arrow above it, is v equals 5 meters per second. The magnitude of a vector is a scalar quantity, and it cannot be negative. Magnitude of vectors are not negative. All right. So at this point, our vector here represents particle's velocity. All right. The displacement vector, straight line connection from the initial position to the final position. Doesn't matter how your particle moves. Let's do an example. This is a good time for an example. Here we go. Here's my starting point. Yes. Here is my particle. It's moving thusly. It's like an 8-year-old or something. Okay. So let's say my particle ends up here. What is the displacement vector for my particle? Well, I can draw it. I can draw it like this. Yes, there it is. That is the displacement vector of my particle. It doesn't matter what it did. Doesn't matter where it went. Only the distance between the starting point. Where's my starting point? Where's my cursor? I can't find it. I lost. Oh, did we? Oh, no, there it is. Okay. Oh no, I lost mouse. Something is wrong with my mouse. That's okay. All right. My mouse disappeared there for a second. I couldn't find it. It was really scary. It's like, where'd it go? Oh my gosh. 2 vectors are equal if they have the same magnitude and direction. This is regardless of the individual starting points of the vectors. They can start from two different points, but be identical at the same magnitude and direction. Doesn't matter where you start from. They can be identical. Very important. But they have to be the same magnitude and pointing in the same direction. Okay, C is the net displacement because it describes the net result of hikers having a first displacement A with the arrow, the vector A, then the displacement B with the arrow above it. Okay, so the net displacement. So we have two vectors. They travel A, a displacement of A, then they travel a displacement of B. We add those two together, tail to snout. Yes, here's the tail of my vector. We'll call this the vector snout. If you line them up, tail to snout, vector snouts. That's a new one. Then our new vector is C. It points from the tail of this vector to the snout of the other vector. I just say that again. Vector snout. A vector snout. What is it? Well, the vector snout is the pointy end of the vector, which points in a direction. Okay, we can add C plus B. We can just add these two vectors together. It's fine. We get a new vector. A plus B gives us a new vector C. Okay. It doesn't matter if A is before B or B is before A. Okay. It's commutative. It doesn't matter. You can add A and then B. Okay. It doesn't matter which way you go. All right. You end up in the same place. It doesn't matter if you go A and then B, because you could go B and then A. You end up in the same spot. See that? It's the same vector. If you go over here like this, putting the pieces of my vector together. It doesn't matter if it's like this or like this. Wait, am I doing that right? Yes. Put it over here. This one, and then this. No, this one. This one. Something is, so I can add A and then B, and I end up, let's put it on my face. Okay, so there we go. So I could go, or I could go over here. I could add B and then A. It's the same place. You end up in the same place. You see what I'm talking about. Moving on, the figure shows the tip to snout rule. Maybe they call it tip to tail. I prefer tail to snout rule of a vector addition and the parallelogram rule. Okay, maybe it's a rule. We can call it tip to tail. Whatever. Parallelogram of a vector addition. Tip to tail rule. D plus E gives you this. It doesn't matter. Tip to tail. Place the tail of E at the tip of D. Parallelogram rule. Find the diagonal of the parallelogram formed by D and E. The same thing. Gives you the same result. There we go. All right. Given vectors B, no, P and Q. P and Q. P plus Q. What is it? I add P plus Q. What vector do I get? Hey, it doesn't matter. At least it shouldn't. No, let's do P first and then Q. So P goes down this way. Q goes over here. The answer is A. It says right there. Makes perfect sense. P, then Q. We start at the same place and end up at the same place. All right. Multiplication by a scalar. If you multiply the vector by a scalar, it makes it bigger. Longer. It's like saying 2 times this vector gives me 2 of this vector. Or if you say 3 times this vector gives me 3 of this vector. Makes it longer. The scaling factor, like you just have C vectors, CA vectors. You add them together, it gets longer. Multiplication by a scalar vector cannot have a negative magnitude. We multiply a vector by a negative number. We reverse its direction. Yes. negative vector, pow. Multiply by -1, pow. Multiply by another -1, pow. Which of the vectors in the second row shows A plus B? Yes, I can do this. I know this one. Let's draw a picture on this one. I am going to draw a parallel of B. Okay, it's gonna be B. I'm gonna put it over here. It's parallel, the same size. That means A plus B has to go like this. That's A plus B, and I'm thinking it's C. That looks an awful lot like C. It is C. There it is. A plus B. Tail the snout rule. Tail the snout rule. There it is. Okay. Okay, erase. To subtract B from A, draw A. Place the tail of minus B at the tip of A. So we've reversed. This was B minus B. Here's B. Minus B looks like this. Minus B. Yes. So A plus B. We've reversed it. Okay. Draw an arrow from the tail of A, the vector A, to the tip of minus B. This vector is A minus B. There it is. We've done it. Okay. Given vector P and Q, what is P minus Q? Well, let me tell you. The minus sign is going to turn Q backwards. It's going to make it backwards. Let me draw minus Q. It looks like that. That is minus Q, ladies and gentlemen. I've done it. Minus Q. There it is. That's a minus Q. It's going that way. And I'm going to move my vector over here. It's going to be a minus Q. There it is. Minus. Oh, no, not that one. I didn't change it. Oh, no, I'm just adding vectors now. Just adding vectors. Okay, so that's going to add up like this. I'm going to put my two vectors together. Okay, I've got a minus Q down there. Let me write minus Q. So this is minus Q. We'll draw the vector symbol up there, minus Q. So this over here, this is P minus Q. There it is. It looks an awful lot like D. It is D. It is D. Remember, whatever happens, don't feel bad because it's easy to make mistakes. You should never feel bad about making a mistake. Mistakes happen. There's troubles in life. What can we say? Every life, there's going to be some trouble. Which of the vectors in the second row shows 2A minus B? Let's get out. Let's draw some vectors. Okay, 2A. All right, here, let's draw 2A here. There's an A. I need another A because there's two of them. 2 times. That means we doubled it. B is pointing down this way. So B is going to go up this way. It's backwards. There's B. That is minus B. Yes. We've done it again. Minus B, the vector. There it is. Minus B. Then I'm going to start here. Draw it up like that. Okay. There's B. There is, what is that? Oh, that's right over here. 2A minus B. It looks an awful lot like A. I'm thinking it's A. Take a minute. Think about it while I erase this. Okay, I'm going to erase this. What is it? What's my vector? It's A. I was right. 2A plus a minus B vector. Minus B gets reversed. Coordinate system and vector components. What are they? What are vector components? A coordinate system is an artificially imposed grid that you place on a problem in order to make quantitative measurements. Quantitative, not qualitative. If it's quantitative, it has numbers. Okay, we will generally use Cartesian coordinates. There are other coordinate systems that are useful: spherical coordinates, cylindrical coordinates, hyperbolic coordinates. We're going to stick to Cartesian coordinates. Polar coordinates, it's real and imaginary. Those are cool. Imaginary. Oh, what is square root of -1? Something to think about. Coordinate axes have a positive end and a negative end separated by a 0 at the origin, where the two axes cross. There's a 0 there. X marks the spots of the origin. We have an angle. So the angle between X and Y is 90 degrees. For vector A and an XY coordinate system, we can define the two new vectors parallel to the axis that we call the component vectors of A. So we have our vector A in the center. It has an X and a Y component. Then if we add them together, if we add AX plus AY hat, or AX vector plus the vector AY, we get A. Okay? You can see, using the parallelogram rule, that A is the vector sum of the two component of the vector A, which is equal to AX minus AY. Okay, there's a minus there. But that's supposed to be a plus. That's weird because they have A there equals whatever. I think that's a mistake, but whatever. All right. I think it is a mistake. You can see, using the parallelogram rule, that A is a vector sum of the two component vectors. Yes, we're going to just, no, go back. Go back. And the mouse is not working anymore. There it is. A is equal to AX plus AY. If you don't believe me, go back to the parallelogram rule. What is it? Parallelogram rule. Parallelogram rule. D plus E equals D plus E. So the vector E plus D equals our new vector. That should be a plus. Should be a plus. All right. Little typo there. It's fine. Just erase that. Okay. Tactics box 3.2. Determining the components of a vector. The absolute value of AX. So of the X component, AX is the magnitude of the component vector AX. Okay, the sign of AX is the positive of AX points in the positive X direction. Negative if AX points in the negative X direction. Okay, the sign of AX is positive if AX points in the positive direction, positive X direction. The Y component AY is determined similarly. Okay, so what does that mean? The absolute value of AX, of the X component AX, is the magnitude, the component of the vector AX. Okay, and AX does not have a Y component. It points in the direction of X. If it's negative, it's pointing the other direction. All right, let's draw negative AX. Negative AX is going this way. Negative AY is going down this way. And I'm trying to erase that. There we go. All right. Moving on. Component vectors can be decomposed into component vectors parallel to the coordinate axis system. If you have a vector A, you can make AY and AX vectors, okay? So we can break it down, and these vectors, AX and AY, are gonna point in the direction of our coordinate system. So if you're on an inclined plane, maybe you're on some plane, then you want to make your coordinate system in the direction of motion. So if you have something sliding down a plane, make your x coordinate system going down the plane. Each component vector can be described by a single number, a scalar called the component. Component AX tells us two things: how big AX is and toward which end of the axis it's pointing. All right, finding the components of a vector. We can find the components using trigonometry. The following case, we find that AX is the magnitude of the vector A times cosine of theta. Okay, that's AX. AY is similarly the magnitude of the vector A times sine of theta. So there's a picture right over here. This is really important. Okay, so the magnitude of our vector A times sine of theta equals AY. These two components make a right triangle, and I always draw them. Okay, so we're going to say that AX is going this way. That's our vector AX. And AY is pointing that direction. Makes a right triangle there, so we can use the Pythagorean theorem. If we know AX and AY, we can find the magnitude of our vector. Okay, so let's erase those. We'll go on to our next slide. All right, if we know AX and AY, we can use the Pythagorean theorem. It's a right triangle. We can get our magnitude, and we can also get the angle. If we know AX and AY, then we can get our angle using arctangent. So if you have a problem where you're trying to get Vx and Vy or AX and AY, then you can use these relationships. Okay? So in a projectile problem, we can get the time to know how long the particle is in the air. Then we can find either our how far it travels in the x direction. Okay, so what's our velocity? How far does the projectile go? What was its initial velocity, maybe, depending on your problem? Okay, so down here in the figures, we see that the magnitude of the vector is equal to the square root of ax squared plus ay squared. And then we have to get the angle, we can use arctangent. So arctangent of ay over ax is equal to our angle. Okay? It works for all different orientations of vectors. Okay, we over here we've got a vector pointing down, so we have c, which is going down, and we've got our angle theta here. This is still, it's still a right triangle. Okay, it's just rotated down. So our trig relationships still hold. Here's our angle theta. Okay, in this case, we get a minus sign here. So this will be minus c cosine of phi, and cy is going to be pointing down. This negative sign tells us that cy is pointing in the negative y direction. Okay, then here, this is our angle. And so in this case, now we have cx over cy. Okay, so cx is opposite to our angle here. And so now we have cx over cy. So think about your triangle. Think about the sides of your triangle. This side is the opposite, even though we're calling it the x component. This side is adjacent, okay? So it's cy, which is equal to minus c times cosine of phi. Okay, and with that, I think we are going to end it here because I think I made my video much longer than I intended. So that is all for now. We will finish chapter 3 hopefully tomorrow. I hope this was useful, and we will see you tomorrow in class. Thank you for watching, and you should be reading chapter 3 and finishing chapter 3 homework. That's available. I also send out an iCalendar link, so you can put that in your iPhone. We won't use Google Calendar since it doesn't seem to be working for everyone. And I think everyone has an Apple device. So I will see you later. Thank you for watching and have a good night.
Thank you. Like and subscribe down below.